So now we've looked at some simple situations of factorising when we've got variable or rational exponents. Let's now take a look at some other situations where we can start using the same sort of factorising laws that we had previously. So let's start with, say, let's go 9 to the power of x take 16. Now, this situation here actually maps back to our difference of two squareds rule. So if you might remember that as when we had a squared minus b squared, that this factorises back into a plus b and a minus b. So if I can rewrite this here to be 2 squareds, I can quickly factorise it back into the brackets like I've got here. So let's try doing that. The very first one here, this 9x, if I actually broke this 9 up, I can say that 9 is equal to 3 squared. But of course, that will have to be raised to the power of x still. And then I can do the same here with my second one. I can say that this is 16. Well, that's going to be 4 squared. So I can subtract my 4 squared at the end here. Now, if I think about this 3 squared all raised to the power of x, applying my power of a power law, I know that I have to keep the base the same, that 3, but multiply the exponents, that 2 times the x. But of course, it doesn't matter which way we could write this. We could write that as 2 times x or x times 2. So I can actually rewrite this to be 3 to the power of x raised to the power of 2 here. Because when I multiply these together, it'll end up with the same result. And of course, this is still subtracting 4 squared. So what I've now got here is I've got a value that's squared, subtracted another value that's squared, which is the same as what I've got here. Except my a in this situation is equal to 3 to the power of x, and my b in this situation is equal to 4. So I can now factorise it into these brackets here, where my a is going to be 3 to the power of x, and it's going to be added with that 4, and then it's going to be 3 to the power of x subtracted with that 4. And as you can see here, I can use the same sort of expansion and factorisation rules that we learnt earlier, even when I've got an exponent here that is a variable. But let's take a look at another one of our expansion rules. Let's take a look at the perfect square situation. Let's say I've got 9 to the power of x, and I add on 4 times 3 to the power of x, and then add on 4 at the end here. Well, what I'm actually going to use here is I'm going to use the perfect square rule that said that if I had a plus b all squared, this is equal to a squared plus 2 lots of ab plus b squared. So if I can represent this in the same format as I've got here, I can move it back to the brackets here. So let's have a go at doing that. The very first thing is I need to work out what my a, or get a number that's squared. So I've done this before. So this 9 to the power of x can be rewritten as 3 to the power of x all squared. So now my a value here is going to be 3 to the power of x. I then look at this here and go, well, I need this to be 2 lots of my a times my b. So my a is 3 to the power of x, I've already got that. I need to multiply this by 2, so it'll be 2 times my 3 to the power of x. And now I need to multiply this 2 by a number to get it back to 4, which will be 2. So I'm suggesting my b value is going to be 2. Now if I look at this one here, I need to write that as being squared. So this is the same as saying it's adding 2 squared. So what you can see here is my a value is 3 to the power of x. My b value is 2, and this is 2 times my a and my b, and I've just forgotten an add sign just in there. Now, because I've been able to rewrite it like this, I can now move it back to its factorised form, where this is a plus my b all squared. So this can be factorised. My a is 3 to the power of x, plus my b of 2 all squared. So what you can see here is even when we've got situations where our exponent is either rational or it's a variable like we've got here, we can still apply our same factorising and expansion rules that we've learnt earlier together with our index laws to be able to factorise these expressions.